Did you know one of the most famous dynamic programming questions is inspired by a staircase? Climbing stairs is a Pattern Mastery 100 classic and a favorite at Google, Microsoft, and Facebook. This deceptively simple problem shows if you truly understand recursion, DP, and how small problems build up to big solutions. Master it, and you'll unlock the core of Fibonacci-style thinking used everywhere in interviews. Let's break down the challenge. You're standing at the bottom of a staircase with n steps. Each time, you can climb either 1 or 2 steps. How many distinct ways can you reach the top? For example, to reach step 4, you could go 1, 1, 1, 1, or 1, 2, 1, or 2, 1, 1, or 2, 2, etc. Now let's assess our approach. A brute force way is to try every path recursively, exponential time. Instead, notice the pattern. To get to step n, you must have come from n1 or n2. So, the number of ways to reach step n is the sum of the ways to reach n1 and n2. This is classic dynamic programming, the Fibonacci sequence in disguise. We can use bottom-up DP or just 2 variables to keep it on time and o1 space. Let's structure our DP approach. If n is 0 or 1, return 1. Set 2 variables. First, ways to reach previous step. Second, ways to reach 2 steps before. For each step from 2 to n, update the number of ways. Current equals first plus second. Move the window forward. Set second equals first, first equals current. Return first. Let's try to implement it using solution 1. Here we're defining a function called climb stairs that takes a number n. This represents how many stairs we need to reach, and we want to count how many different ways we can climb to the top. We create a map called memo. This is our memory box. We'll store answers we already computed so we don't redo the same work again. That's the memoization part. Now we define a helper function called DFS, which takes x. You can think of x as how many stairs are left to solve. This function will return the number of ways to climb x stairs. This is our base case, the simplest situations. If x is 1, there's 1 way to climb, just 1 step. If x is 2, there are 2 ways, 2 single steps, or 1 double step. So for x less than equals 2, we can immediately return x. Before we compute anything, we check if we've already solved x before. If memo already contains the answer for x, we instantly return it. This avoids repeated recursion and saves a lot of time. Here's the main idea. To reach stair x, your last move must have come from either x, 1, a 1-step jump, or x, 2, a 2-step jump. So the number of ways to climb x stairs is ways to climb x, 1 plus ways to climb x, 2. This is exactly like the Fibonacci pattern. Now we save the computed result v into memo under the key x. So next time we need DFSX, we can grab it instantly instead of recalculating. And we return v, the number of ways to climb x stairs. This closes the DFS function definition. Finally, we call DFSN to solve the original problem, the number of ways to climb n stairs. Time complexity note: because we memoize, each value from 1 to n gets computed once, and each computation is constant work. That makes the overall time complexity on. And that's how this algorithm works. It first sets up a memo storage to remember solve subproblems, then it recursively computes the number of ways using DFSX, 1, plus DFSX, 2, while caching results to avoid repeated work. Efficient, simple, and elegant. Let's test our function using this input, n equals 2. This number represents the total number of steps in the staircase, and we're counting how many distinct ways we can reach the top if we can climb 1 step or 2 steps at a time. Here's why the solution works. The DFSX function returns the number of ways to reach step x. If x is 1 or 2, we already know the answer. It's just x. Otherwise, the total ways is DFSX, 1, plus DFSX, 2, because you can arrive at step x from either 1 step below or 2 steps below, and the memo map just stores results so we don't recompute them. For this test, we call DFS2. Since 2 less than equals 2, it immediately returns 2. That matches the 2 valid paths, 1 plus 1, or 2. And that's exactly what our program outputs, 2. The code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully counts the number of ways to climb 2 steps using 1-step and 2-step moves, efficient and accurate. Now let's try another implement approach using solution 2. Here we define a function called climb stairs that takes n, the number of steps in a staircase. The goal is to figure out how many different ways you can reach the top if you can climb one step or two steps at a time. Time complexity. O(n) because we build answers step by step up to n. This is our quick base case. If there are one or two steps, the answer is just n. For one step, only one way. For two steps, either 1 plus 1 or 2, so two ways. So we return immediately to avoid extra work. Now we create an array called dp with length n plus 1, filled with zeros. This array will store answers as we go. dpi means how many ways to reach step I. We make it n plus 1 so we can use the index n directly. We set the number of ways to reach step 1 to 1, because there's only one way. Take one step. We set the number of ways to reach step 2 to 2, either 2 1 steps or 1 2 step. Now we loop from step 3 up to step n. We're going to fill in the dp table from the bottom up, meaning we use smaller answers to build bigger answers. This is the key Fibonacci style idea. To land on step I, you can only come from step I, 1 by taking one step, or step I, 2 by taking two steps. So the total ways to reach I is the sum of the ways to reach those two earlier steps. That's why it behaves like the Fibonacci sequence. This closes the loop. By now, dp3 through dpn have all been calculated. Finally, we return dpn, which is the number of ways to reach the very top step. And that's how this algorithm works. It first handles tiny staircases with a quick return, then builds a dp table from the bottom using the rule ways to step I equals ways to step I minus 1 plus ways to step I minus 2. Efficient, simple, and elegant. Let's test our function using this input, n equals 3. This number represents a staircase with 3 total steps, and we're counting how many distinct ways we can reach the top if we can climb one step or two steps at a time. Here's why the solution works. We use a dp array where dpi stores the number of ways to reach step I. We start with the known base cases. dp1 equals 1. dp2 equals 2. Then for each step I from 3 onward, we add the two previous results. dpi equals dpi 1 plus dpi 2 because you can arrive at step I from either one step below or two steps below. For this input, we compute dp3 equals dp2 plus dp1 equals 2 plus 1 equals 3. That lines up with the three valid paths, 1 plus 1 plus 1, 1 plus 2, and 2 plus 1. And that's exactly what our program outputs, 3. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully counts the number of distinct ways to climb 3 steps using dynamic programming, efficient, accurate, and reliable. Breakdown recap. We started by understanding that each step can be reached by taking either 1 or 2 steps from below. So, the problem is really about counting how many unique sequences of 1s and 2s can add up to reach the top, essentially, finding all possible combinations to climb n steps. Assess recap. We compared different approaches and noticed that brute force recursion tries every possible path, which grows exponentially. Instead, we discovered a pattern. The number of ways to reach step n is the sum of ways to reach steps n1 and n2, just like the Fibonacci sequence. Structure recap. We structured a simple dynamic programming solution by building from the ground up. Starting from the base cases, we iteratively calculated the total ways for each step, storing only the last 2 results for efficiency. Implement recap. Once we coded it up in LeetCode, the implementation ran smoothly without any issues, efficient, clean, and easy to read. Check recap. We tested the logic using LeetCode's built-in cases, confirming that every input passed successfully and the results matched our expectations. The key takeaway is that many complex problems simplify beautifully once you recognize the recurrence pattern. In this case, climbing stairs wasn't just about movement, it was about understanding how smaller subproblems build up to the complete solution.